Welcome. This is the second part in Chapter 5. The title of Chapter 5 is Learning, and the second part is about genetic algorithm, part of our course in Intelligent Computing in UPM. So let's start with the concept of learning itself. You know now that the machine learning is a concept that in AI that allows the pattern recognition is identified based on the examples. And you know that there are two learning approaches. First is the inductive learning and the deductive learning. So last week you have looked into how decision tree can be developed based on inductive learning. So in the exercise last week, you have constructed the decision tree by identifying attributes that have the most data coverage, and then you edit the tree by splitting it into branches to capture the most accurate representation. This slide shows the concept of the genetic algorithm, which has the name entails, is an example of evolutionary computation. On the right side of the slide, you can see the flowchart of the genetic algorithm. While in the slide also introduced to you about several analogies of biology, which are used, such as population, genes, chromosome selection, reproduction, offspring, and fitness. Right, let's proceed to the specificity of each genetic algorithm concept. The chromosome is a way to encode the representation of information. So binary is an example of representation. 0 to indicate false. So if you could recall the last week's exercise from the table, then 0 can be representing no or false. 1 can represent true or yes. Then the selection is a technique used to identify parents for reproduction, as well as the splitting points, where later in the reproduction, two operators can be applied, the crossover and mutation, as the fitness is a measure of the strength of the chromosome. Then the operators, the crossover. If you see in the picture there, the dotted lines indicate the splitting points. So crossover is the exchange of the parts between the identified chromosomes. Then mutation allows us to swap some parts in the chromosome. So all these are to be able to generate better offspring based on the reproduction. This slide repeats to you the steps in the genetic algorithm, and this is actually a repetitive process until the termination condition is met. Example of termination condition is when the number of generation is met or the fitness function becomes worsened. I'll utilize two examples to guide you further. Let's say that you are given this challenge. Let's say you are working for Kai, who is on a project on fundraising event, and she has to pitch to generous funders. So the generous funders are the members of BTS, and you are assigned to assist her with identifying the best combination of funders to meet so she can maximize her collection. And assume that there are challenges such as the logistics and also time and the probability to meet each of the funder to pitch. So this is an optimization problem to identify the best combination. So we start with genetic algorithm. The first step is to initiate the population. Let's say that a constraint is being used to focus on 3 funders only. And we assume this is the determination criteria, and we create the population. So randomly, we can identify 3 combinations. Let's say Jungkook, Jin, and J-Hope from this table. So this is represented by 111 because we have Jungkook, Jin, and J-Hope, and the remaining are not selected, so we assign 0. As for the second chromosome, to generate C2, we identify Jin, J-Hope, and Suga. So Jungkook is assigned 0, Jin 1, J-Hope 1, further V0, Suga1, Gmin0, and RM0. Similarly with C3 and C4. So these are the initial population or chromosomes in the formulation. Next step is to identify the fitness function. So we learned that the fitness is the total of the funding in each chromosome. So this is done quite easily to combine what are the total funding by each of the identified funders. Then we want to perform selection. To ease us to process this further, I have copied the chromosomes from the previous slide as well as the table shown on the right side of the slide. Now, let's say we decide to perform crossover of the two fetus chromosomes, C3 and C4, and we set that the position for splitting is at point number 3. And we want to mutate C2 on the every even position gene, and we want to remain C1. So we perform the reproduction. We cross over C3 and C4. So look at the original C3, 001, 0011. The original C4 is 0000 and 111. So we identify the first 3 points in C4, which is 000, to replace the 001 in C3. So this is swapping as for the crossover. For the mutation on C2, we mutate every gene at even positions. So we get 0010100 and we remain C1. This generates offsprings, which becomes the prime, tagged by prime. Then we update the population and evaluate the fitness value. Based on this, we discard C4 prime because this is not complying the rules since 4 people has been selected. So this leaves us with the set of new population in the new generation. Next, we continue with the next generation. I copied step 5 again to ease your progress. And C4 prime is removed, and we replace the parents with the offsprings. So left us with only 3 chromosomes. Then we want to continue the learning process, and we perform reproduction. So from this, we cross over 2 fetus chromosomes again, while actually the identification of the reproduction is up to you based on your strategy. As long as the operation and the concept of genetic algorithm is applied, then that's fine. So the operation in step 6 have produced C1 prime and C3 prime as well as C2 prime. We evaluate the fitness again. From this, we discard C3 prime because this is not complying the rule, and we are left with C2 prime, which returns that the total to be collected is 50,000 by approaching V and Suga. Well, you might argue why this time that the result is getting poorer, only 50,000. Now you have seen the generated suggestions as lower than the previous generation. And you might also identify that this process is tedious and slow. You might also think, why not just create rules and let's say only combine top 3 funders. This is exactly the intention of this lesson, to show you the difference between rules based and the GA. So next, let's explore further the advantage of GA. You might suggest different selection or reproduction strategy as listed in the slide. So let's say for step 6, we perform the reproduction differently. We cross over C1 and C3 and we use a different splitting point. So we will generate new offsprings. Then the mutation also is done differently, although on C2, but we specify that the gene at the position 3 and 4 will be mutated, and we want to also perform mutation on C1. Then we evaluate the fitness value. So from this, again, we identify that C3 prime needs to be discarded because it does not comply the rule, but we get a better output because the fittest chromosome is C1 through the combination of J-Hope, Suga, and Jimin. So Kai could raise 110,000. So that is done with the first example. This is now the second example. Now Kai is playing the role as the advisor of a student club, and she has collected this information. And you are asked to assist her to identify the rules that contribute to someone obtaining first class. You might think that you have seen this table before. Exactly. So I want to illustrate to you how genetic algorithm can be used to solve the same problem. Remember, the first step is to initiate the population. Oops. First step is to initiate the population. So to simplify the attributes, I've used acronyms here, and I've changed the to WH, DR, FTY, and FLY. Then I use chromosomes with 0 and 1s again, and I randomly created 4 rules, which in my assumption would be the best 4 to cover the data. So in my first chromosome, I said that FLY is yes. FLY is yes, male is yes, WH is no, DR is no, and FTY is no. And the same with the continue with the other chromosomes. So from this, I now go to the next step, which is to identify the fitness function. And I copied from the previous slide to ease you to continue the process. Then here, the fitness function is based on this. You want to identify the examples, the rules that can parse more than 60% correct of the examples. Again, this fitness function is based on your determination. But based on this one, we can identify the score of C1 on Richard. So this chromosome 11010 can parse Richard 5 out of 5, meaning all the combinations are correct. For C2, for C1 on Ellen, only matches 2 genes out of the whole 5, and then Allison only 1 matches, and so on. From this, I can count what is the number of score that is more than 60% correct. So I got the fitness score for each of the chromosomes. Now I want to continue with step 3, which is to perform selection. I want to apply crossover on 2 fetus chromosomes, C1 and C2. And I set the splitting position as well as the other operations on the remaining chromosomes in the population. From there, I perform reproduction. So C1 prime now becomes 10110 because from C2, the first 2 genes are copied to replace the original 2 genes in C1. Then the green table is filled up again. So C1, for C1, 3 out of 5 because we have 1. So matches with FLY is Y. Then second is 0. So this one does not match. Then 1 here does not match again. And then 1 match and N match. So we get 3 matches. So this is 3 out of 5. Then continue to fill up this table and then count the fitness. So from this, we have the results. Since the fitness value is decreasing, then the learning can be stopped and C1 is returned as the best solution. Well, to summarize and conclude, genetic algorithm provides a way to learn and model the best representation of the data by evolution, and the randomity and the possibilities can also be evolved. However, this is a slow process, although has a good advantage to be able to identify and tune the best output. With that, I thank you.